Hi everyone, today we're going to be continuing from where we ended off last time from k-means, and we're going to be talking about Gaussian mixture models and expectation maximization. So Gaussian mixture models, as I talked about a little bit last time, is a way to generalize k-means, and expectation maximization is something that we haven't talked about yet, but will be used to kind of formulate the k-means algorithm for more general models. It's a very powerful model that's used in a lot of machine learning algorithms, and this is the only other way you can kind of solve a problem besides using gradient descent, which is something that neural networks and other discriminative methods use. So before we start though, we have to talk about a little bit about probability theory, because Gaussian is a probability distribution. A Gaussian or a normal distribution is a continuous distribution, and it looks like this. I'm sure a lot of you guys have seen this. It's also known as the bell curve, right? The bell curve, right? And here is its center of mass, which is also called the mean. And remember, by the way we denoted mean last time, we denoted it as a mu, right? And the variance here is kind of like how far the bell stretches. So if it stretches like this, or like this, that's this like variance, or standard deviation, which is the square root of its variance. So we can say that this is a standard deviation, which is denoted as sigma. Okay, so why does it look like a bell curve? So actually, this distribution is currently only under one variable called x, and this y-axis here is actually the probability of it occurring. So so it makes intuitive sense that when something's near the middle of your distribution here, it's more likely to happen, right? It's like when you get your test scores back and you're at the average of your class. More people are in the average than on the sides, like the ones who like break the curve or get like zeros on the test. So here we can say that y is the probability, and thus it's also equal to p of x. Okay, this is a continuous distribution, so usually we say that like if something, okay, so this is the total probability theorem. And this total probability theorem means that everything must sum up to 1, as in 100%, right? So if you have a bag and it has a red ball and a blue ball, right? The probability of it having a red ball or the probability of it being a blue ball, these two events are disjoint. You can't have neither or both when you take out a ball. So these are individual disjoint events. So that's why we can say like plus as in or, right? This has to be 1, right? Because what else is there in the bag? You know that you took out one ball, and that means that it's 100% chance either red or blue, right? So this is a very discrete case because we have two items in here, right? But in the case of discrete / countable. In the case of Gaussian or normal distribution, we see that this is actually every number on the number line, right? So for the Gaussian, it looks like this. The summation, the integral, right? This is the area underneath the curve of p of x dx from all the way on the left to all the way on the right is equal to 1, right? Because the probability of something falling under any number between negative and infinity and infinity will be greater than 0 but less than, the integral of all the probabilities will have to be equal to 1, or else like you're missing a number or you added too many or something like that, right? So here, this is infinite items. So like imagine you taking some balls out of the bag and there's infinite, well, in this case there's like uncountably many infinite items. I don't want to get into whether it's uncountably infinite or countably infinite. It's just like real numbers versus integers. But let's not get into that. I'll just say infinite slash infinite uncountably. And this is also a continuous distribution. This RV means random variable, and random variable is just the x, so it's just a variable. And that variable, when we have a probability of that variable, it's going to give us our probability. Okay, and one more thing is the Gaussian distribution actually looks like this. So if we have an x is in the distribution, normal or Gaussian, of mu and sigma squared, we have the probability of x is equal to, now this looks very ugly, but don't worry about it. Well, like it doesn't come out to be this ugly later. 1 over the square root of 2 pi sigma e to the negative 1/2 x minus mu squared over sigma squared. So this looks kind of intimidating, but all you need to know that this sums to 1 when we integrate it. And yeah. Oh, and one note is that sigma squared has to obviously be greater or equal to 0, right? Because it's squared, and also like it's the amount of which it goes, like the amount of which the number varies. You can't vary negatively, right? So if you have a very big variance, it means that your bell curve may look like this instead, right? Okay. Okay, so how do we generalize this to a higher dimension? Well, we can just kind of draw the Gaussian in 2D and kind of see what is going on. So Gaussian in 2D really looks like this. And actually this is where the Gaussian actually is motivated from. So we have an x and we have a y, right? And the probability, I'm going to say, is going to be marked by a circle. So like probability will look like this. Oops, the audio cut off for a minute, but pretty much I just want to draw circles that denote the probability at a certain value. So say at this point, probability is probability of x and y is going to be, say, 0.7. And here, everything along that line, probability of x and y is going to be equal to, say, 0.3, right? And then here it'll be x and y will be, say, 0.1, right? So these are just contour lines. These are called contour lines, or isocontours of the 2D Gaussian. Now, if we kind of generalize what we said before, where we have a mu and we have a sigma squared, right? Now, now if we draw this out, it looks like we have, so following from the same picture as last time, we have this kind of Gaussian on the y-axis and this kind of Gaussian on the x-axis, for example, right? Then we can kind of draw circles like this, that kind of denote the center of the probability, right? And this is where exactly where k-means and Gaussian mixture models actually differ, because in k-means, remember that we use this in our k-means, right? But what about this one? This is not used, right? But this could be some very valuable information. And also, if both of these axes are independent, it means that this circle, no matter what you draw it as, it's eigenvectors or it's principal axes will always be snapped to an axis. So it'll always look like this. Like this and this will always be like horizontal and vertical. So instead of saying a variance, we now need to have covariance. So our covariance is going to be kind of denoted as a capital sigma this time. And it's going to be the variance of, say, x squared, variance of y squared, right? And if these two elements are 0, then it looks like this. But if it looks like something like this, because it's symmetric, we now have a different looking circle. It will then look like maybe something like this. Because in this case, we're saying the variance of every element varying on this axis, right? And on this one, we're saying the variance of everything varying on this axis, right? But what about if x and y are very similar? Like say if this was weight and this was height, right? Then that means that they're very correlated with each other, right? Then that means that these things will not be 0 because this will be probably positive if they are correlated. So this term is called covariance, cov of x and y, and it basically means how much things kind of relate to each other. So if weight and height are very similar to each other, then that means that you'll get a very correlated, like positively proportional relationship between the two. So you might be wondering, Ray, why are you telling me all of these things about Gaussians? I don't really need to know them, right? Well, of course, our algorithm is called Gaussian mixture models. So then here we have to incorporate some properties of Gaussians inside of our model. And to kind of explain, just to recap, in our k-means algorithm, we had k centers, or mu's, right, to kind of center our clusters together. But we assumed that all variances are equal. And also, all of them are equal to the identity matrix times a specific variance. And what do I mean by that? If we kind of say that everything has the same variance, we come out to have, say, this is the mu of x, this is the mu of y, and now we have a variance. Since both of them vary by the same amount in all directions, we have a circle for our isocontour. So it just looks like a gradual circle radiating out with the same probability every time. And all of our means will look like this. And as a result, we have some very linear decision boundaries. I'm not going to explain exactly why, but you can kind of see it by visualization. So say this is another cluster, and then we kind of radiate out from here. We radiate out from here, right? You can see that there's this line right here that kind of says like, oh yeah, on this side it's one cluster, and on this side it's another cluster, right? But now we're going to have a Gaussian mixture model, which is going to give different variances, right? Now this time, this is not going to be true for our GMMs. And as a visualization, it's going to look like this. Let's see, I'm going to use red for this one. So maybe it looks like this, right? And then we have another cluster, say here, and let's use blue this time. And maybe it looks like this. and this one has a closer dense probability than the red one, right? Then obviously their decisions are not going to be exactly linear in like, as in like everything on one side is in one cluster and everything is on the other cluster. So maybe this time it kind of looks like that or something, right? Like maybe that even, right? So as a result, we kind of need to create a more complex model by saying that the variances do not have to be equal. So how are we going to get over this problem by kind of just estimating our variance? It's going to be a very hard problem. So this is where our expectation maximization algorithm comes in to solve the GMM model. So this comes to our expectation maximization algorithm. So this is a little introductory proof for it. It's not very hard. We just need to know maybe like one identity of convex optimization and then we're done. But pretty much we assume that our data has probability of labels, which is Z, as in like the clusters. And here we're trying to maximize the probability of our D as in data, right? And what is our data? Here we have X only, right? This is an unsupervised setting, so we have X but we don't have Y, right? And we're trying to maximize the probability of X happening, right? And say when you're trying to maximize the probability of X happening, you know that we have n data points. So we want to maximize the probability of n data points happening, right? So we multiply all the probabilities together and we try to maximize that amount, right? Because if everything has probability of 1 happening, then that means that 1 times 1 times 1 times 1 times 1 will give us 1, and that will be the maximum probability we can ever achieve. And so that's what we have here, which is trying to maximize all n points, right? And this is just a trick that like pretty much happens in all of machine learning architecture and literature, which is they take the log probability. Because we know that multiplying things of very small value, say like 0.1 times 0.001 dot 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 dot, and then we do this like 100 times, right? This will give us a very, very small value. And in computer science, at least, this will give us very inaccurate floating point accuracy. And so we don't want to do that. And also, obviously, multiplying takes longer time than adding in a computer, so we want to add instead. So taking the log of everything makes it less unstable and also faster. And it gives us the same result because maximizing, say, something that looks like this. This is, say, x, right? And maximizing log x, right? Looks like it's always increasing, right? So at the minima of x, we also get the minima of log x. And at the maximum of x, we also get the maximum of log x. So a very complicated function can be turned into a log, and we can still take the maximum of it. Does that make sense? Okay, cool. So this is the very famous log trick that everyone uses in like a bunch of other algorithms other than expectation maximization. So now that we have this area, we can kind of say that the total probability theorem states that if we have xn and we have labels zn, right, and we have to sum up all possible labels of zn, this will give us probability of xn. Why is that true? We can just refer to the total probability theorem, prob theorem, right? Because when we sum up everything from taking our bag, we get out 1, right? But here we're just multiplying kind of the probability of it being xn by 1. Just a little illustration of why this is true. If we have, say, x and z here, right, and we want to know the probability of x, right? Well, if everything was situated on a grid like this, right, and then we have like some other points here or something, right? If we sum up every point here, we get the probability that x is equal to this, say x naught, right? In like proportion to all of the other points that are in our probability function, right? Because we have a proportion of a lot of circles inside of this column where x is equal to x naught, and thus the probability of it will be proportional to how many circles there are inside there. And that's the same idea as taking blue and red from a bag, because whether it's blue or red, say this is a blue z and this is a red z or something, and then we go on, everything, whether it is blue or red, doesn't matter. The only thing that matters is that x is equal to x naught, and we get out the probability of x naught there. This is a very hand-wavy explanation of it, but hopefully it makes sense. Okay, so now that we have that, we can kind of substitute this in for the using the total probability theorem. We get that it is equal to, and from 1 to n, log of Zn, probability of xn, Zn. Right. Okay, now this looks very ugly. And it is ugly because we have a sum inside of a log. We can't take that out of a log. It'll become a multiplication and it will end up looking very ugly, and we can't really minimize this very fast. So one trick that everyone does is the following. It's called Jensens inequality. It's a little thing from convex optimization, which states that if f of x is convex, then f of expected value of x is always greater than or equal to the expected value of f of x. And then the expected value is defined as the summation of p of x times x. And here, we don't really have that p of x here, so we're going to add in a p of x inside of this term. So now our equation is going to look like, now we'll continue this on the next slide, log sum of Zn. Now we're going to have this another probability distribution that we just came up with for like we don't know what it is yet, but we're just going to add it in there. Q of Zn, P of xn Zn divided by Q of Zn, right? Because we multiply, we divided, it's really equal to 1, right? And so this is actually the expected value of P of xn Zn divided by Q of Zn. And by following this rule that you blindly just follow because I don't have enough time to prove, we will say that this is greater than or equal to the summation of n is equal to 1 n log, whoops, can't write log right now because we're going to apply the inequality, Zn. Now we're going to have log of, no, actually, not yet, Q of Zn log of P of xn Zn over Q of Zn, this entire thing inside of the log. So this is our result from the last slide. And now we're going to continue. So we know that this is a lower bound, right? Because before we said Jensens inequality states that expected value of f of x is less than or equal to the f of expected value of x. Right? This is Jensens inequality. However, now I'm going to introduce another fact that you don't need to prove because it's pretty trivial actually. We just need to say that f of e of x will equal E of f of x if x is proportional to P of x. And proportionality just means that this P of xn, zn, is going to be proportional to Q of zn. Because then we can just say that, oh, sorry, actually that is not true. If x is a constant, some constant c. And for this statement, we can have that it will be equal to c, because if we say that it's proportional to, right, then we say that P of xn, zn, is going to be c times Q of zn, right? Then we have P of xn, zn divided by c, divided by Q of zn, right, from this statement. Then we just get c here, right? Then that means that this statement will be true, right? This is true if this part, right? Then you don't need to know why I do this, but oh yeah, just a side note, everything here is already like proved, and this is a valid algorithm, so you don't really need to worry about why this is true. But the things that I left out are actually very trivial, and you can look them up online if you really want to. For example, the constant thing, or Jensens inequality, which is a natural follow-up from convex optimization. You probably learned that in like the very beginning. Okay. Now that we have this, it looks a lot nicer to deal with, right? So then we have, if we say that Q of zn is some distribution that's proportional to P of xn zn, then we have some, right, we just plug in c times Q of zn, right? So we have Q of zn log c times Q of zn, right? And here we have, it's just equal to Zn log c, right? But here we shouldn't just say, oh, it's okay, we're done now, because now we actually need to know what this Q is, right? And obviously, from what we just said before, it's proportional. So yeah, so now we know that Q is proportional to P of xn zn here, this statement. We know that we can just kind of plug in P of xn zn as well. So then we get an equivalent statement of, well, actually before I go on, Q of zn is a probability mass function, or probability density function. Then that means that Q of zn must add up to 1, right? And if it's proportional, then we say that Q of zn, this sum zn, is equal to 1, right? And we say that Q of zn is like some constant of P of xn zn, right? Then we can kind of say C times P of xn zn is equal to 1, right? Now we know that this probably does not equal to 1, right? Because, like, obviously it's not equal to 1, because we only summed up over one axis, right? So if you look at this, x and z, we only summed up like this side, right? So like if there were other points here, then that would not be 1. So now the key point is, how do we solve c, this c here, such that it's equal to 1, because we want a valid probability distribution? Well, it follows that if Q of Zn, if we say that Q of Zn is not normalized, then we can kind of divide Q of Zn by all possible values of Q of Zn, right? To get like something that is an actual probability distribution. Because if you think about it, this just means what fraction of q of zn is it to the entire q of zn summed up together? And if you have one component, the second component, the third, all the way up until the last component added up together in this fraction, then it's going to be representative of everything inside of this sum. So we get 1. So this is going to be an actual probability, right? And another way we can phrase this is p of xn zn over the sum of zn p of xn zn, right? Because this is a fraction of what the what the sum is. And following the total probability theorem, we see that this is equal to p of xn zn over p of xn given zn. Now, you don't really have to follow this part, but it's just to help you understand. But now that we have this, we can see that this is actually the C term, because this normalizes everything such that we get a constant inside and Q is a probability distribution. So now, just to recap, we have the joint, the P of xn zn divided by P of xn given zn, so we can normalize it. We can then use, this is a rule from probability theory called Bayes' rule. It's not too difficult of a theory, but you can just look it up online if you're interested. But pretty much it means that you can break up a joint into a conditional, and then we can express this entire expression as P of zn xn. And then we get that Q of xn is equal to P of zn given xn. Then to rewrite everything, we have the summation from n, the summation from zn, right? Probability of zn given xn times the log of probability of zn and xn over probability of zn xn. So then recall what we started with. What did we start with? We started with the probability of data, right? And then we also took the log of it here, right? So this entire bulky thing is our probability of our data. We call this the complete expected likelihood. Likelihood just means the probability of something happening, right? And expected because we don't really know what this thing is, but we just said it was this. So we expect it to be this. So this is not like something that you can just use to solve everything. But in an unsupervised setting, this is very powerful because you don't really need to take a lot of derivatives and solving and like trying to bound your parameters so then they don't go out of bounds. But yeah, this is the EM algorithm's first part. And this is what we calculate. This is our first step, right? So remember in our title we have expectation, right? This is the expectation. So this means we expect likelihood of our data to be this, right? And what do we do in machine learning? We try to maximize the likelihood happening, right? Because if it happens a lot, then that means that our data is representing our model is representing the data very well. If we can kind of predict the next event happening, that's machine learning, right? So here we're going to maximize this, right? Maximize this. So how do we maximize this? Well, actually, this is our next step, so maximization, right? Our algorithm's name is expectation maximization, and this is where it comes from, right? This is just taking the argmax of our parameters, I'm just going to call it theta, of this log P of D, right? And this is a very condensed version of this entire expression, right? I'm not going to show the entire derivation, but it turns out that for Gaussians, you just pretty much compute mu k is equal to the summation of p of zn given xn times xn divided by the summation of this is n and this is, oh actually this should be zk. Oh actually this is zk, that's xn. zk, xn, and for a specific k we don't need the second summation. Yeah. And now we have n p of zk xn, right? So this is kind of like the average. If you think of this as 1 or 0, right? What do we get? We get the k-means algorithm back. Do you see? Because when we said this was in k-means, we have this y(n)k) times xn over n y(n)k). Remember that? Right? Well, what did we just replace? We just replaced y and k with a probability. Y and k before was equal to 1 or 0, right? Now, this new y and k is going to be a probability of zk happening given xn, right? And so this is like kind of pretty much just translating what k-means is into a more complicated model, right? And now our sigma k, we also need to calculate this, right? And it turns out that it's going to be the probability of zk given xn minus mu k xn minus mu k transpose divided by the summation of n p of zk given xn. And one more parameter is this omega k, which is pretty much saying the probability of z happening in general. So this is just like anything between. Okay, actually, it's not anything because we're trying to maximize it. It is the probability of zk given xn divided by the probability of n, zn, probability of zn given xn, and this entire thing is going to be equal to n, right? So it's going to be n probability of zk given xn over n. And why did I say all of these parameters? Well, in our expectation maximization step, we will use all of these parameters. Let me just write it in the next slide. Mu k, sigma k, and omega k. What do they do? Well, recall that our equation looks like this. I'm just going to draw it out very, very quickly. And then log p of xn zn, and now we're going to say this is going to have three parameters: mu, sigma, and omega, and then we're going to have the p of zn given xn here. And in this portion, we're only trying to maximize this joint, maximize this. And we're trying to keep this constant. Because what we do in the expectation step is to calculate our likelihood, right? So our log p of d, right? And here, as a result, we calculate P of Zn xn. We have P of xn given Zn, P of Zn divided by P of xn. And this is equal to that via Bayes' rule. And you can look this online if you want to, but it's pretty obvious. So you get this expression is equal to this P of Zn given xn. And so this is going to be our observation, right? So just to illustrate, it's going to look like some points here, right? And say our initial cluster looks something like this here, right? Now, what is the probability that this cluster is going to be like right here, given your points, right? So here, this may be the point that's assigned to these points, these red points, right? That's their membership. Well, obviously, if you kind of draw some points out of these circles, it looks like this center is not doing a very good job, right? So it's just saying, like, how far is it from what you have as actual points, right? And that is where we calculate this part. And then afterwards, we move this over, kind of like k-means. So we get this graph. And then we're going to calculate our new distribution such that it's going to be closer, so it'll be right here. And these are its clusters, so it'll do a very good job, right? And because we don't explicitly create this ourselves, we use all of our distributions from our previous guess, right? These are previous, like old news, right? Right. Then we want to compute the new parameter such that this center is going to be there, right? So the center is going to be mu k, and the variance is going to be sigma k, right? And the omega is just like the probability of this cluster happening at all. So if you're coding this by yourself and wanting to come up with like a very concrete algorithm, here's a list of what you should do. So 1, just like k-means, actually let's call this step 0 because it's not really a step. 0, initialize mu k, sigma k, and omega k to some random values, random. But remember that sigma k has to be positive semi-definite. So maybe just make it the identity matrix. And also omega k has to be in 0, 1. So maybe choose 0.5 or something like that. And this mu k and sigma k are going to be in a normal distribution, and this omega k is going to be inside of this categorical distribution, and this is going to be p of xn given zn, and this is going to be p of zn, and together they form p of xn zn. Remember that term inside of our log? So it's like log of this over log of zn given xn, and then p of zn given xn, right? So this is going to be contributing to this term. And you can compute everything else from that too. So we get this, these distributions, and what we do is we say step 1, we take we calculate membership. This is kind of like k-means, right? But however, now it's not going to be 0 or 1, as in like the closest cluster has the closest points. Now we're going to give it a probability, right? So what is the probability? We're going to calculate p of zn given xn, right? And this is equal to p of zn and xn divided by p of xn given zn, right? And we have everything we need here, right, to calculate that. Because this is the joint that we can calculate from both of these. And this one by itself is the denominator. So we get this probability, right? So we calculate this. And then step 2, then we recompute, as in maximize. So this is the expected step, and this is the m step. So now we maximize likelihood, expected likelihood. And that's going to be when we calculate mu k is equal to blah blah blah, sigma k is equal to blah blah blah, and omega k is equal to blah blah blah. This is from the previous slide, right? And you do E, then M, then E, then M, and dot 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 until it converges. And that's pretty much the entire algorithm. But we had to set up a lot of complicated machinery here to kind of get our to get this issue of not having a probability of Zn to be and then we solve it. So this is the EM algorithm, and it's very powerful, and it calculates k-mean clusters that have different sizes and shapes. And it's a lot more expressive than the normal k-means algorithm. And if you have a lot more data, you should definitely use this model over k-means, because this one will give you better results. Thank you.